Please join me in welcoming Brent Gorda from ARM. I'm not introducing as normal, so you get to have the podium.
I get to introduce myself.
Yeah, well, Brent is good.
Half the people here know me. It's good to see friendly faces. Maybe we could get some more friendly faces up front. And no. Don't even get a reaction out of some of them. Oh, good, I have a timer. Thank you. Okay, so Brent Gorda, I work for ARM Incorporated. ARM is an up-and-comer in the HPC space. I am an old guy in the HPC space. I first was introduced to seismic processing in the late 80s and attended a conference or attended a talk where someone stood up and said, gee, these microprocessors are really kind of cool, but what would happen if we used multiple of them? And I got hooked in parallel computing in 85, 86, something like that. And that's led to a very long career in high-performance computing. I grew up in Canada, Calgary, the boots, the oil, all that. I actually have a picture of me in a rodeo, but I couldn't download it in time. I didn't realize the rodeo was in town. I was going to show you me riding a bull, which I have done. And a long career in high-performance computing, predominantly as a user. I was at the national labs at the Lawrence Livermore National Laboratory, participating in the phase change from vector computing to parallel computing. Some of the old guys remember vector computing, and it's come full circle now. We did a lot of work then in trying to define what it means to run in parallel, and a lot of that is still in use today. Along the way, I did a number of startups. The one that I'm most known for, I think, is a company called WAM Cloud, which wrestled the Lustre technology out of Oracle using the GPL and kept it relevant to this community. That experience was probably the most fun position I've held and ended up in a sale to Intel where I spent 5 years at Intel doing HPC storage things. Hi, Nash, put your phone down. And you're taking notes, okay. I did a couple of other projects that have touched this community that are at least a little bit tangentially interesting. In the late 90s, I did a project called Software Carpentry, and I invite you to go to softwarecarpentry.org. That is a project that is a not-for-profit that intends to teach, or intended at the time, it's since grown beyond our initial intent, intends to teach scientists, people who understand science, how to use computers so that they're not wasting the time on these $100 million systems that we buy. And that's exploded to the point where there's more than one class held every day of the year. And it's had forks off of that for data carpentry and other things. So that was a really cool thing to be involved with. And then the second project that I've worked with for this community is something called the Student Cluster Competition. And that started out in '07 in Reno at SC, and we decided we would bring in undergraduate students to build up a cluster and run these open source apps that we run. And it was mostly a statement of everybody's getting gray, we need younger blood, and these kids coming out of college now are completely capable of running with the equipment that we use, at least on the lower end. So that's kind of my background in high performance computing. So what am I doing at ARM? I also worked on the Blue Gene project, right? Now my friends from previous lifetimes come to me and say, are we really going to be running HPC on cell phones, right? Everybody here knows ARM as the company for IoT and cell phones. We're not really going to be running on cell phones, maybe with respect to the ISA, but not with respect to the technology. So an introduction to ARM. Outside of HPC, ARM is a pretty big force. Your cell phone likely has an ARM processor in it. Much of IoT is ARM processors. ARM does the design for the silicon and then licenses that design to companies that want to build an embedded product or build mobile products. That's generally the bread and butter. The volume on these devices is astronomical. Last year alone, there were 21 billion ARM chips, ARM-based technology chips sold. What that means is that the process for silicon design is optimized around the ARM intellectual property, right? That carries forward and affects us in high-performance computing. We design the IP, we don't manufacture any chips. We partner with people, and I'll talk a little bit about what that means for high-performance computing. The partners build their products, be it from your refrigerator to your cell phone and now to your server, and we support them in that. We think choice is good. For the last 10 years, our community has been focused on one architecture. And with this entry of ARM into the market, what we do is we permit not only one other architecture, but we permit anyone who wants to license the ARM ISA or the microkernel to build whatever they want with a very solid basis. And I'll get into that a little bit. HPC is a very good spot for this to be going on. One size doesn't fit all. So about those cell phone processors. This is a slide from about a year ago from a system called Isambard at the University of Bristol. It's a Cray-based system. And what you're seeing is a comparison of performance per socket, where higher is better, and the ARM-based processor, which is a Thunder X2 from Marvell, Cavium Marvell, is leading the way in many of these applications. Now, this is a socket-to-socket comparison, so you can get down and look at the number of cores and so on, but these are server-class products. These are not cell phone-class products. These are server-class products. And they're in use today, and they're coming at you with full force. A bit more on our business model. ARM is way off on the left end there. We build IP that we license. The licensing is quite complex, and there's quite a bit of a pick list of things that you can license from ARM. Our silicon partners then take that, and they put their special sauce on it. So when HPC goes to Fujitsu and says, we really, really, really want more memory bandwidth, Fujitsu comes out with the AFX64, A64FX, with a terabyte of memory bandwidth. That's a Fujitsu design, that's not an ARM design, right? Fujitsu has put in those memory controllers and that HBM2 on top of the chip, and then they go to fab with that. Fujitsu is responsible for taking that to market and using it, in this case, the Post-K machine. And you're going to learn a lot about the Post-K machine because Satoshi is here tomorrow. Satoshi's the director at Riken who is buying the Post-K machine. I would pay a lot of attention to any numbers that he chooses to release. He's really good at announcing things that aren't quite there yet. I would follow him on Twitter, for example, because he's announced that the TDP for the node for the Fujitsu machine is 170 watts, which is super low for a node in an HPC system. And every time I hear him talk, I learn a little bit more about these designs. You can tell by the way I'm talking, I'm not in deep with that particular project. It turns out that you can license the ARM technology and you can go off and do your thing with it. You don't need to interact with us. You don't need our permission other than the ISA and passing the platform tests to make sure you're compatible. You can go implement it how you like, and that does happen quite a bit. So Marvell, Fujitsu, Huawei's the other one up there, Ampere, there's a bunch of them now that have licensed ARM and are off building. You will read about the exascale designs, two of which are currently based on ARM, or rumored to be based on ARM, one well actually three, the Fujitsu chip, the Phytium chip in China, and then the European Union indigenous processor design is suggesting an ARM platform. So then the chip manufacturers approach the platform designers, HP, Cray, and Atos are the big ones right now, and they build up a system, and finally it gets deployed to the end user. The reason ARM is so special here, not just because we show up at the far left with the IP, but we also show up at the very bottom. We do a huge amount of work in software and helping the community build up the software ecosystem. You don't go anywhere without software these days. There's another name I want to drop. John Masters is from Red Hat, and he is particularly interesting in that he dragged Red Hat into the ARM camp, and the reason Red Hat works on ARM is because of John's efforts. Very interesting character, very interesting character. In fact, John will say hardware doesn't matter because the software is so good now that you can just run on that platform and that platform. And to first order, the applications guys aren't going to care because the performance is going to be similar, better this way, better that way, and the compatibility is there. So a lot of that is credit to the software ecosystem. This is currently the largest public ARM-based system. It's installed at Sandia National Labs in Albuquerque. It's number 203 in the top 500. Integrated by HPE and chips designed by Cavium, now Marvell. I was lucky enough to go down and see the ribbon cutting for that system, which was interesting because I got to see a whole lot of old colleagues from the Department of Energy and a lot of excitement over the fact that this is a different architecture, but much more over the fact that it just worked. Every new system, being involved in a lot of new systems at Livermore and Berkeley, every new system has issues. And the resounding noise out of the users for these ARM-based systems are, we just compile and run. It was a 2-day effort. Now, we all know that you can spend the rest of your life optimizing for that same platform, but the fact that you can be out of the box and running in a couple of days is huge. And that was, I joined ARM a few months before supercomputing, and at supercomputing, I quizzed all of the sites, all of the users, and it was consistent across the board. We just compile and run, it just works. I think a lot of the secret behind that was that ARM bought the Alinea Software Group a few years ago, and the Alinea Software Group makes software tools that are cross-platform. So if you're already working with their tools and they work on x86 or Power, they're just going to work on ARM. It's a matter of an LLVM backend for the target architecture. So you can read the stats there. It is the Apollo 70 with a Mellanox interconnect. Other recent announcements. Cray installed the Isambard system at the Met Office, which is the upper left. Atos CEA has one. Pretty much all of the big DOE labs are toying with it, playing with it, because everybody is interested in how it looks, feels, tastes, that sort of thing. There's a big project in the UK you should keep your eye on called Catalyst, which is an HPE project with the Marvell Thunder X2. 3 universities there are building up clusters and giving access to their researchers and helping to mature the software stacks on that stuff. There's also an interesting press release between the NNSA lab, Los Alamos, and Marvell that has to do with roadmap design that I would draw your attention to. The software ecosystem, this chart could be almost any architecture because it all is just working. I was in Japan a couple of weeks ago, and Satoshi Matsuoka, who again will be here tomorrow, credits the compliance test that ARM has with the Fujitsu chip booting up and running Red Hat Linux first week. So this stuff just works. Like John Master says, the hardware doesn't matter. Where it's going to matter is when it comes to efficiency and when it comes to cost and when it comes to process design. We just heard a whole lecture on running out of steam and Moore's law and process design and when we get to 5 nanometer and all that sort of stuff. Well, guess what? The mobile industry is quite capable in pushing those technologies forward, and they've got a vested interest in it. And once again, high-performance computing gets to leverage the broader market and take advantage of what's going on over there. I don't think there's a whole lot to call out about this. We're members of the Open HPC organization, and so we support everybody we can. I will point out that we don't do all of this work. We do the tools and compilers for the most part, but there are 3 public sets of tools and compilers the Fujitsu tools and compilers, the ARM tools and compilers, and the GNU tools and compilers. Did I miss one, John? No? Yeah, Cray does not have an ARM the Cray does have an, sorry. I was thinking of a different, yes. So there's 4 sets of tools. The Cray tool set all works on top of ARM at this point. Okay. The HPC apps that we all have grown to know and love are all porting over to ARM and in various states of comeuppance. Pretty much they're all working. I'm looking at John to nod his head. And in the continuous cycle of let's see how fast we can get this stuff to run. So it's all mature stuff. It's all running. We've got a community web page, and we're inviting users of the systems, people interested. It's open. You can come check out what's going on these sites. So all of the basics that you would think of for standing up an HPC community, we're trying to do all that with a bit of a different business model. Keep your eye on the different business model, because it's, when you hear of an ARM supercomputer out there, it's really a ARM IP, Marvell chip, HPE integrated supercomputer out there. It's not that ARM builds these things, okay? That's critical moving forward, because you can get a branch in the architecture, not from the ISA point of view, but you can get a branch where if there is enough interest in machine learning and machine learning specifically wants a different technology in there, they can go build it themselves. One of the secret sauces, listening to the questions from the last talk, one of the secret sauces that ARM is bringing to bear here is an instruction called the SVE instruction, which is the Scalable Vector Engine, I think is what SVE stands for. And that is you think of the AVX 512, ARM has basically an AVX 256 to 2048 instruction. You don't need to recompile for this. The architecture gets to implement it at its own desire. And it's one of the knobs that the HPC community and the AI community are studying quite deeply. Fujitsu has chosen a 2x512 instruction. So it's a 2-unit 512-bit SVE. Others are looking at broader instructions, and so you'll be able to get much higher vector performance on the chip itself. Satoshi will talk tomorrow about the comparison between the Fujitsu chip and the GPUs from NVIDIA. Because with that much memory bandwidth and that much vector capability, you can really crunch out a whole lot of data. Okay, I want to shift gears a little bit here. Last fall, we introduced a new brand name called NEOVERSE. NEOVERSE is, again, a flexible architecture that's pointed at data center and high-performance computing and gives you these system knobs to turn where the vendor can decide how many cores they want, all the way down to 4 cores if you're doing an embedded design for some sort of edge compute, all the way up to 128 or 256 data cores. Cache, bandwidth, all of these things are tunable by the vendor, and then the vendor also gets to add their secret sauce around that. So we're lifting the game a little bit with respect to the core technology that we're licensing out, and the vendors are taking those parts and building bigger and better things with them. What's frustrating is not to be able to hint a little bit more at the roadmap. So if you care about HPC, if you care about new technologies, I invite you to go get an NDA with Marvell, who's sitting in the room waving at you right now, Larry. Go get a discussion going with them about what the roadmap looks like, and you'll get a bit of an eye-opener with respect to where things are going. Our roadmap, which again is the design roadmap, that was announced and valid up until last week. So there's a bit of an Easter egg here. Nobody gets to leave the room now. Had us jumping from 16 nanometer to 7 nanometer, promising a 30% performance gain per generation and turning this crank once a year. So we're upping the speed with respect to what we can produce for our partners. I will skip that one. Our first maybe I won't skip it. Our first announcement from this next step in the Aries design is called the ARM N1 and the ARM A1. Notice the performance per watt. One thing that I don't think I've stressed here is ARM's history is coming from a very energy-constrained, performance-dominated environment. So the IP created at ARM, some of it is built to sit in a battery and run for a year on a battery. So exceptionally efficient designs, and that's going to... So that energy efficiency gets to bubble all the way up to HPC, and that's one of the reasons that the exascale designs are looking at an ARM architecture. NEOVERSE sits alongside ARM Cortex. So the very far right is the Cortex designs, the Cortex 56, 72, all of those designs. That's what everybody thinks of as ARM. That's all the embedded stuff. That's all the cell phones, mobile, that sort of thing. Everything to the left of that is a new brand called ARM NEOVERSE. And in the short time I've got left, I'll give you a teaser of that. At ARM, we believe that in the next 10 years, there will be 1 trillion edge devices, 1 trillion live licensed ARM Cortex and competitors out there, all of which are trying to send data upstream over the internet to the cloud centers. We think that breaks the internet. We think that there's a re-architect of the internet going on, and that will happen in the next 5 years. It's going to be a very exciting time, and we're in the midst of it, providing IP design to handle the mass amounts of data to the edge, the fog computing that you've heard of, and then further on to the cloud data centers and to high-performance computing. So we are going cross-spectrum on this, expecting that there's a phase change about to hit us, and it's going to be super interesting. Going from sending cat videos to your phone to sending surveillance videos back upstream is a very different world. So trillions of devices. At the edge, we're working hard on having AI capabilities so that your video camera on the side of your house makes an intelligent decision as to what data it recognizes and or sends upstream to your cell phone or to the edge compute. So filtering at every layer here and computing at every layer. So computing is being pushed outward, more network is being brought back, and the data centers are fundamentally changing. Last December at AWS reInvent, I'm looking at AWS over here for nods to make sure. December at AWS reInvent, Amazon announced 3 things that I think are interesting to the HPC community. The first one that's the broad announcement is a processor called the Graviton processor, and it was available immediately, and you can run it alongside your x86 instances, rent it by the hour, and run much of your workload on it. There was the claim of either 30 or 40% price reduction. You guys should have sat together. Was it 40% price reduction for certain workloads? Okay. So what that is that's AWS now getting into the silicon game, which is super interesting, right? Imagine what a big company with super deep pockets and a vested interest in controlling their own destiny, having licensed ARM IP. Imagine what goes on there, that they can do. And I'm not in the know, so I can blissfully talk about it. The other thing they announced, and I won't remember the name, but they announced a kernel bypass messaging system. So all of a sudden, low latency kernel bypass protocols are available to you in AWS. And then the third thing announced that's near and dear to my heart is support for the Lustre file system there. So the Graviton processor is not an HPC-oriented SKU, but you could easily imagine if there is a lineage of those coming at us, that they might at some point become interesting to HPC. They've already got the networking, they've already got the storage. I think there's some interesting things going on there. Okay, so what was announced last week, I already talked about the ARM NEOVERSE N1. ARM turns out to be, their background is they're a British company, they're very conservative. They announced whenever we announced this, November, after SC, of course, because HPC doesn't get the first news. They announced this 30% pipeline. Last week, they announced that the first step of the pipeline was a 60% performance gain, and they're still promising 30% per year thereafter. So we think this is an interesting roadmap. There will be further announcements coming out about people jumping on board with the N1, Ares, and Zeus. And we are busy, the HPC arm of ARM, are busy getting the word out to communities like this and partnering with the folks that really want to see a different architecture show up and have the ability to help us push that forward. And I think I will take questions at that point.
So thank you for mastering that microphone drop. So questions? So I do have a question, actually, even while others are thinking about it. So you brought it up. You mentioned that licensing is complex. Yeah, turn it on, I guess. Did you turn the button on? No, it's on.
Yeah.
So what I wanted to follow up is actually, so ARM to some degree is like Uber. Uber invented rideshare, ARM invented sort of open IP. But now what about RISC-V? And you said licensing was complex. There's a lot of article written around the whole RISC-V, and maybe licensing is kind of be your challenge. So how do you deal with that business model?
Well, the RISC-V technology, there's a couple of things going on there. Yes, RISC-V is predominantly open, but if you want to build a complete system, you actually do have to license things and pay for things. The bigger concern with the RISC-V is that the software is a huge, heavy lift. ARM has been working on the software with both internally with this Linero company and with the community for years and years and years. Unless the RISC-V community can conjure up that amount of effort to get the software together where the next RISC processor will just boot Red Hat, I think it's a steep climb. Now, note with RISC-V, I don't believe that there's a platform-ready requirement. So you can make a chip that's not completely compatible with the last chip, and it's not going to run any of the software. So I looked at RISC-V quite deeply when I was considering where I was going to go next, and all of these things came up and were presented as challenges.
Question. We have one here. Microphone is coming.
Lots of I/O, Chin. It's got huge I/O.
Don't worry. I know that. I just wonder, as a cluster HPC software vendor, any particular commodity hardware supply is the one we should be talking to? HP seems to be the one you mention most often.
HP and Cray and Atos are the big
Cray is
ones.
not something that typical small software startup can buy.
No, well, if you're talking about a software startup that wants to go out and port their code, for example,
Yeah.
there are a number of cloud providers that will give you the ThunderX2 chip if you want the performance. You can go to AWS and get the ISA and just port software to the ARM environment. And then when you need to go test it for performance, you move over to some of the cloud providers that give you the ThunderX2.
That still doesn't give us the full control because we need the control of the storage, of the computing side, which you cover, or cloud provider will cover, but we also need networking too.
So the networking is there. The storage isn't, right? As a storage guy myself, I know that storage is always an afterthought. None of these performance benchmarks.
Yes, you see, you even have to...
Hear about the IO 500 here from DDN, but
so
it's certainly incomplete. It is up and coming. It's literally months old, single-digit months old.
Okay.
But it's maturing, and requests like this, I invite everybody to reach out and say, gee, the ARM ecosystem...
I know where to find you, don't worry.
You do.
I know the mic will operate. Any other questions? If not, let's thank Brent.